Hello everyone, my name is Bharti Kanade, Enter IT System. I'm going to explain first internal of data science using Python. Part 1. Statistic characterization of contained data. Question number: give three commonly used statistical measures to characterize the dispersion and complete diverse scores. First, the three commonly used measures of dispersion. First, range, maximum, minimum, simple, sensitive to outliers. Interquartile range removes the outliner, disguise spread of middle 50%. Standard deviation SD equals to 1 upon 1 minus n summation of x n minus x bar square. Sample SD. Measure spread around mean useful when data are approximately symmetric normal. Efficient computation over large contained repositories streaming algorithm. Well-formed algorithms for mean and variance memorize the stable single pass. Approximate sketches, t-digits all q-digits for quantiles, fast and manageable across partitions to compute medians. Approximate sketches, Palatinate aggregation, compute partial statistics partitions, then merge. Reservoir sampling, for random sampling, when data set too large to store, then compute exact measures on the known sampling error. Histograms for codes approximators for distribution and median. Question number 2. Sorted average strength scores 1 to 100 extracted from the content text. Sorted value 13, 15, 16, 16, 19, 20, 20, 21, 22, 23, 25, 25, up to 70. What is the median score? What is the median? What is the com, comment on modality? What is mid-range? First, mean and median. Mean equals to sum of values 20 upon 27 equals 29.96. Median. Median value of, of the score is 27. The fourth value equals to 25. Mode. Frequency is equals to 25 appears 4 times. 35 appears 4 times. 16 appears 2 times. And 20 appears 2 times. 22 appears 2 times. 33 appears 2 times. Other ones. Mode equals to 30 and 25. Both highest frequency 4. 4. Binomodal distribution. Mid-range. Mid-range equals to 1 plus max upon 2 equals to 13 plus 70 divided by 2 equals to 41.5. Estimate question number 1 and question number 3. Using the usual 25 and 75 sample point quantiles, question number 1 equals to 20.5 and question number 3 equals to 35. Minimum equals to 30. Question number 1 equals to 20.5. Median equals to 25. Question number 3 equals to 35. Maximum equals to 70. Box plot description. Box from 20.5 to 35 with median line at 25. IQR equals to 14.5. Whiskers using the common rule 51.5 into IQR equals to 21.75. Lower fence equals to 1.5 into IQR equals 20.5 minus 21.75 equals to minus 1.25. No lower outliners. Lower whisker equals to min equals to 13. Upper fines equals to question 3 plus 1.5 into IQR equals to 13.35 plus 21.75 equals to 56.75. Values is greater than 56.75 are outliners. Up to 70 is an outliner. The upper whisker is the largest non-outliner, which is 52. So the box plot shows the cluster in the 20 to 25 range, a big wheel, long right tail, and one clear outline at 70. Q to Q plot versus quantile plot difference and use. Quantile plot plots quantile level. It shows how the data quantiles change with probability, useful to visualize the distribution shape. Q to Q plot plots quantiles of your sample against quantiles of theoretical distribution or normal sample. If sample quantiles align truly, On the 45 line, the sample follows the theoretical distribution. Use Q to Q to test whether evidence shows follow a particular target distribution assumed by the DSS. Use quantile plots to visualize the distribution form itself without directly comparing to the reference distribution. Severity index distribution. Range 1 to 5, 16 to 15, 16 to 20, 21 to 50, 51 to 80, 81 to 100. Frequency 200, 450, 300, 1500, 744. Total cases 13, 3194. Median position equals to 3194 divided by 2 equals to 100, 1597th observation. Cumulative frequencies per Ben equals to 2200, 650, 950, 2050. Median lines in the 1, 21 to 50 bin. Interpolated inside the median bin. 21 to 50. Lower class found L equals to 21. Class width equals to 30. Cumulative before bit equals to 950. Bin frequency 1500. Median equals to L plus N by 2 minus cumulative before divided by F bin into width. 21 plus 1597 minus 950 divided by 1500 into 30. Answer equals to 33.94. Approximate median severity equals to 33.9. Interpretation typical complaint severity is in the 30 to 55, 30 to 35 range. Code. A district intake sample records complete age and self-assessed incident impact percentage for 18 complaints. Age percentage. Data equals to n equals to 18. Age equals to 23, 23, 27, 27, 39, 41, 54, 54, 56, 57, 61. Impact percentage 9.5, 7.5, 17.5 to 1335.7. A. Compute mean and median and standard deviation. N equals to 18. Mean age equals to 14.6, 46.4. Median age, middle of sorted, equals to 51 years. Impact standard deviation 13.22 years. Mean impact in percentage 28.7%. Mean impact in percentage 13.70%. Standard deviation is equals to 9.25%. Fox plots. Lower fence equals to 18.25. No outliners 26.75%. Outliners 9.5% and 7.8% are below the lower fence. Two outliners very small self-assist impacts. Largest outliner box between 33.75%. Median equals to 30.7%. Scatter plot and Q to Q plot to study relationship. Scatter plot. Visual check for relationship for this data. Pearson correlation correlation is equals to 0.8.8. Interpretation. Older complaints tends to report higher self-assessed impact percentage in this sample. On this scatter plot, you would see points roughly following an upward trend. You could fit a regression line impact percent equals to A plus B dot H to summarize the trend. Q to Q plot. Q to Q for normality. Draw Q to Q plot of ages versus normal quantiles and impact percentage versus normal quantiles to assess approximate normality. Ages. Some self-screw checks if checks points roughly online, if so normal approximation okay. Impact percent presence of two low outliners will produce departures in the low tail on the Q to Q plot. Q to Q between variables. You can also Q to Q one variable versus another, less common to check if they share distributional shapes. Part B. Similarity and dissimilarity in feedback. Briefly outline how to compute dissimilarity between students' feedback profiles described as normal attributes, asymmetric binary attributes, numeric attributes, term frequency vectors. First, normal attributes. Example, jurisdiction, police station, offense category, etc. Dissimilarity rule. If values match, distance equals to 0. If values differ, distance equals to 1. General formula. For k nominal attributes equals to d ij number of mismatches upon total nominal attributes. Notes. Using simple matching coefficient alternative assign a cost matrix if some mismatches are more serious. B. Asymmetric binary attributes. Example, criminal force present, property damage present. Presence divided by absence of elements. Here, 1 equals to presence is more important than 0 equals to absence. Use the zeroth distance. Let Q equals to position where both R1, R positions where I equals to 1, J equals to 0. S equals to positions where I equals to 0, J equals to 1. Zcard similarity Q divided by Q plus R plus S. Zcard distance equals to 1 minus Q divided by Q plus R plus S. C. Numeric attributes. Example, incidence duration, estimate loss, age counts, severity scores. Distance used, Manhattan. Pre-processing normalization, numeric values Z0 or min max to avoid scale imbalance. D equals to summarize mod xi minus yi. D equals to summarize xi minus yi h divided by 1 by h. D. Term frequency vectors from FIR text keywords entities of its elements represent components as TF or TF-IDF vector. Distance measures cosine distance D equals to minus x dot y divided by mod of x divided by mod of y. Jacquard for sparse bag of words. Question number 6. Distance computations between tuples. Given A equals 22, 1, 42, 10. B equals to 20, 0, 36, 8. Representation included, included distance equals to 6.708. B. Manhattan distance equals to 22 minus 20 mod plus mod 1 minus 0 mod plus 42 minus 36 mod 10 minus 8 equals to 2 plus 1 plus 6 plus 2 equals to 11. Minkowski distance h equals to 3. D equals to 2, 233, 233 equals to 6.13. D. Supremum distance. D equals to max delta xi minus y. X yi. Difference is 2162. D delta equals to 6. Question number 7. The median score is often a key holistic indicator of faculty or infrastructure performance when dealing with massive student feedback datasets. Proposed method for median approximation analysis their complexity and suggest to balance accuracy versus efficiency. Median approximation in large datasets. Median is robust for triage. Exact median is expensive for massive databases. Approximation methods. GK quantile summary maintains an approximate quantile summary space. O big O 1 log E. Mergeable works in distributed DSS. D-digest maintains centroids with small variance very accurate around median space less than 5 kb for millions of points. Measurable map reduce friendly. Third, reservoir sampling. Sample k observations uniformly from streaming complaints. Compute median on sample error 1 by root k. Time and space complexity summary. Method, time, space, accuracy. Exact sorting O and login. Big O and exact. GK summary. Big O login per insert. Space Z. Big O 1 by E login. E approx. E approx. T digest. Big O log K high. Reservoir. Big O 1 insert. Big O K median. Heuristics use GK or D Digest for accuracy. Use reservoir sampling for extreme scale. For distributed system, combine partial summaries. Always remove outliners before computing median. Question number 8. Consider student faculty similarity analysis. Complete. F1, F2, C1 1.5, C2 2, C3 1.6, C4 1.2, C5 1.5, F2 1.7, 1.9, C3 1.8, C4 1.5, C5 1. Query vector equals to 1.6 to 1.4 to 1.6. Let's compute distance to each complaint. Complaint P1 equals to 1.5 to 1.7. Root 1.5 minus 1.4 square plus 1.7 minus 1.6 square equals to 0.141. Manhattan mod 1.5 minus 1.4 plus mod 1.7 minus 1.6 equals to 0.2. Max cosine similarity equals to 1.5, 1.4 plus 1.7 multiplied by 1.6 divided by root 1.5 square plus 1.7 square root multiply root 1.4 square plus 1.6 square equals to 0.998. Cosine similarity equals to 0.998. Complaint 2. 2 to 1.9 equals to 0.6 square plus 0.3 square under root equals to root 0.36 plus 0.09 equals to 0.671. Complaint 3. 1.6 to 1.8 equals to root 0.2 square plus 0.2 square equals to 0.283. Manhattan equals to 0.4. Supremum equals to 0.2. Cosine similarity equals to 0.992. Complaint 4. C4 equals to 1.2 to 1.5 equals to 0 under root 0.2 square plus 0.1 square equals to under root 0.05 equals to 0.224. Manhattan equals to 0.3. Supremum equals to 0.2. Cosine similarity equals to 0.987. Complaint 5 equals to 1.5 to 1.0. Under root 1.1 square 0.0.6 square equals to 0.608. Manhattan 0.7. Supremum 0.6. Cosine similarity equals to 0.93. Similarity ranking. Similar, smaller equals to more similar. C1 0.141, C4 0.224, C3 0.282, C5 0.608, C2 0.671. Manhattan, same order as elucidation. Supremum, same order. Cosine larger equals to more similar. First similar, first C1, second C3, third C4, fourth C2, fifth C5. Normalization of all vectors to unit length and recompute distance. X rays equals to 0.658 to 0.752. Normalize all complaints. Below are the results. Complaint. Normalized vector. C1 equals to 0.664 to 0.748. C2 equals to 0.724 to 0.690. C3 0.664 to 0.747. C4 0.625 to 0.780. C5 0.832 to 0.554. Recomputed distance from X dash. Complaint. C1 equals to 0.0098, C2 equals to 0.0099, C3 equals to 0.0290, C4 equals to 0.0830, C5 equals to 0.2450. Final normalized ranking. First equals to C1, second equals to C3, third equals to C4, fourth equals to C2, fifth equals to C5. Question number 9. Discuss accuracy, completeness, and consistency issue. First, accuracy. For accuracy, first consider a recommendation system for online purchase of clothes. When it comes to birth date, this system may or only care about in which year the user was born. so that it can provide the right choices. However, app in Facebook which makes birthday calendars for friends must acquire the exact date on which a user was born to make a credible calendar. Second, for completeness, a product manager may not care much if customers' addresses information is missing, while a marketing analyst consider address information essential for analysis. Third, for consistency, consider a database manager who is two big companies' information databases into one. When he decides whether two entries refer to the same movie, he may click the entry, title, and release date. Here in either databases, the release data must be consistent with the title or there will be annoying problems. But when a user is searching for a movie information just for entertainment, user either database whether the release date is consistent with the title is not so important. A user usually cares more about the movie's content. Two other dimensions that can be used to assess the quality of data can be taken from the following timeless believability, value added, interpretability, and accessibility. These can be used to assess quality with regard to the following factors. Timelessness. Data must be available within a time frame that allows it to be useful for decision making. Second, believability. Data values must be within the range of possible result in order to be useful for decision making. Valuated. Data must provide additional values in terms of information that offsets the cost of collecting and accessing it. Fourth, interpretability. Data must be not be so complex that afford to understand the information it provides, access the benefits of its analysis. Question number 10. For handling missing values in expected features, discuss approaches, ignore tuples, manual completion, constant fill. The various methods for handling the problem of missing values in data tuples include first, ignoring the tuple. This is usually done when the class level is missing. Task involves classification or description. This method is not very effective unless the tuple contains several attributes with missing values. It is especially poor when the percentage of missing values per attribute varies considerably. Second, manually filling in the missing value. In children, this approach is time consuming and may not be a reasonable task for large data sets with many missing values, especially when the value to be filled is not easily determined. Third, using a global consensus to fill in the missing values, replace all missing attributes values by the same constraints such as a label like unknown or minus infinity. If missing values are placed by, say, unknown, then the mining problem may mistakenly think that they form an interesting concept since they all have a value in common, that of unknown. Hence, although his method is simple, it is not recommended. D. Using a measure of central tendency for the attributes such as mean, the median, or the mode. For example, suppose that the average income of an electronic customer is 2,800 that the data are symmetric. Use this value to replace any missing value for income. Fifth, using the attribute mean for numeric values or attribute mode for the nominal values for all samples belonging to the same class as the given tuple. For example, if classifying customer according to credit risk, replace the missing value with the average income value for customers in the same credit risk category as the of the given tuple. If the data are numeric and screwed, use the median value. Sixth, using the most probable value to fill the missing value. This may determine the regression interference based tool using Bayes formation or discussing tree induction. For example, using the other customers' attributes in your dataset, you may construct a decision tree to predict the missing value for income. Question number 11. Smoothing extracted scores. First, smooth using bin means with bin depth 3, show steps. B. Suggest a way to detect outliners. C. Discuss other smoothing methods. First, smoothing using bin with depth 3. Smoothing using bean means so group the shortest list into consecutive bins of three items each and replace each value by its bean mean. Mm, Bin consecutive triplets and their means. Bean 1 13, 15, 16 mean equals to 14.667. Bean 2 16, 19, 20 mean equals to 18.33. Bean equals to 3 20, 21, 22 mean equals to 21 point. Bin 4 20. Bin 5 25, 25, 30 mean equals to 26.667. Bin 6 33, 33, 35 mean equals to 35. Bin equals to 8 36, 40, 45 mean equals to 40. Bin equals to 46, 52, 70 mean equals to 56. Smoothest series. Smoothest series, each original replaced by its bin value 14.667 to 56. Notes: smoothing reduces local noises and emphasizes board structure. Use rounding to approximate precision for the system. B. Detecting outliers. Approaches. First, statistical rules. Second, robust methods. Third, model-based residuals. Fourth, density. Fifth, rule-based domain. Sixth, force score correlation. Seventh, action when an outliner is detected. Statistical rules. Z equals to score Z. 3 as outliners. Robust methods. Median absolute deviation. Model-based residuals. Fit expected impact from features. Density. Points with much lower density than rivers. Fifth, rule-based domain. Very high financial loss with zero evidence or no witnesses. Cross-source corroboration. If claim is high impact, no matching records in EFIR. Forensic CCTV. Mark unparable. Seventh, action when an outline is detected. Mark for human review. Attach province check. Maintain separate treatment in modeling. C. Hybrid. Combination of forward and backward add features, occasionally remove previously added ones if they become redundant. Pros. Balance cost and ability to handle interactions. D. Filter method. Use univariate measures. Fifth. Embedded methods. Regulations methods that shrink coefficients to zero. Tree-based feature importance. Rank features. Fifth. Wrapper methods. Use classifier as black box and sort subsets. Sixth, dimensionality reduction (PCA CVD) for numeric features or truncate CVD for TF IDF text features. That was the whole solution of internal one that I explained in this video.